Hello, everybody. Welcome to the Stats for the Masses webinar, Overview of Logistic Regression. My name is Elaine Eisenbeisz. I'm the owner and principal statistician here at Omega Statistics. I'm sorry for the late start. We were having some little technical glitches, but I think we've gotten them all worked out. So I want to thank you for taking the time to join us live. In fact, thanks to everyone for their interest in our webinars. I really enjoy putting these together. Today's going to be a lot of fun. You'll see in a little bit. But today I'm going to present a very simple overview of logistic regression, and we're going to cover when to use the logistic model as well as the assumptions that you need. We're going to run through the steps of running a model and interpretation of the findings, and we're going to use SPSS. Today is just an overview, but I hope that the information you receive today will give you some ideas and guidance on how to make use of the logistic regression in your research. As I say in all of our webinars, use what you learned today, apply it in a holistic way, think about the big picture, not just the how, but the why of your study. Your big question should be when you get your results, gee, what does this all mean? And try to figure that out. So as always, it's my hope that if nothing else, you're going to come away from today's presentation feeling a bit more in control of your capabilities as a researcher. So I'm hoping to cover the presentation in about 40 minutes today so that we may have some time at the end for some Q&A, which would be great. I think you might have a lot of questions today. I currently muted the line, so only my voice can be heard, but our statistician assistant, our assistant statistician, Brianna Ramirez, is monitoring the chat board. So feel free to type any questions you have on the chat board, and then Brianna will choose some to ask me at the end of the presentation. She's also going to assist you if you have any technical problems that you might experience. One thing I found that if you do have any technical issues, if you just log out and log back into the webinar, it seems to clear up just about anything. So I always say when in doubt, reboot. So let's see what we have here with our slides. Here we go. Well, I always like to tell you a little bit about Omega Statistics. For you that come to, all of you who come to every month's webinar, you see this every time. Probably should change it up a little bit. But for the new people, we're a private practice statistical consultancy. We're based in Southern California. We do medical and clinical research, so we help with clinical trials, we help with big studies in epidemiology, large data sets, journal article assistance. Maybe you have some statistics from your study and you need to write it up for a journal article, you need some analysis, we're the people to call. We also do exploratory design and predictive modeling. We help with dissertations, the methods and the results chapters. Survey design, we help with projects of any size, so small, large, individual researchers, large corporations, government contracts. Our motto is to provide elegant solutions effectively applied. So let's get started. And the big question is, what is logistic regression? I always like to show the textbook, and then I like to show our Stats for the Masses definition too. Logistic regression, it's a statistical model for analyzing a data set in which there are one or more than one independent variables that determine an outcome. So that sounds a lot like a regression, except with a logistic regression, the outcome is measured with a dichotomous variable, and that means there's only two values, and it's coded 0 and 1. It's pretty much just like a regression, but the outcome has yes, no, true, false, either or, happy, unhappy, things like that. A logistic regression can be applied to outcomes with more than two groups. It's called a multinomial regression. We won't be covering that or the other types of regression today. We're just going to look at that dichotomous outcome with a 1 and a 0, either or. There's ordinal regressions, Poisson regressions. I mean, there's probably one for every day of the year maybe. Why use a logistic regression? Well, it depends on the question you're asking. And as I was putting the data together for the presentation today, I was thinking, what kind of data can I put together that might seem interesting, that might seem fun? And I got my idea from a dinner that we had with friends. My husband, Rod, and I went to see some friends last Saturday for dinner. They had just wired their house for the internet, Netflix, so you could get it on any TV. So we went and watched some movies. And as we were looking through some choices on Netflix, and under the husband's name, everything, were all these choices for Tom Selleck. Tom Selleck in this movie, and Tom Selleck in oh, I don't know, he's in a thing now. What is it, Blue Bloods or something like that? And so, we were teasing him about it. Gee, Mark, is there something you need to tell us about Tom Selleck? But so we teased him about it most of the weekend, on and off through text and such. So I thought, well, what a neat thing to do. Let's kind of build this around a Tom Selleck fan club. So if I wanted to, I could say we have two groups of people. We have some people that are in the Tom Selleck fan club, and then we have some people that aren't in the Tom Selleck fan club. And we want to maybe test to see if there's a difference in the mean ages between those who are in the club and those who aren't. And for something like that, we'd use a t-test. And we would get our mean ages of those who belong to the Tom Selleck fan club and compare them to the others. However, a logistic regression kind of turns that around. What if I wanted to know if a person's age predicted membership? It would predict whether or not they were in the club, and basically would it predict if they were a member. Then a logistic regression is the test to use. Another thought is, what if you wanted to know if a few variables were associated with membership in the Tom Selleck fan club, and how important are each of these variables? Maybe some are more important than others. And now we're in regression territory, and so the logistic regression would definitely be your test to do something like that. So why not use ordinary least squares regression, also called a multiple regression? I just call it regular regression. Why not just use that? Well, an OLS regression uses a continuous dependent variable. It means your outcome has to be continuous, like age, weight, something like that. And the assumptions for using those OLS regressions relate to that continuous dependent variable. We have a best fitting line right here. This is an ordinary least squares, and I think we covered this last month. We make the best fitting line through all the data, okay? And then we have to measure our error to that line, and then we can kind of get an information for your model fit from there. So we don't have that with dichotomous variables. You're either going to have a 0 or a 1 on your outcome, and nothing in between. And the line is, well, like I said, linear, right? We don't have that with the dichotomous variables. Also with a dichotomous dependent variable, we don't have the ability to check assumptions of normality or homoscedasticity. Homoscedasticity absolutely relates to these distances, and we don't have that. So it kind of falls apart on us. Here's the scatter plot and residuals plot from an OLS regression when we did use the dependent variable of being a member in the Tom Selleck fan club. And as you can see, there's nothing linear in this scatter plot, right? And there's nothing scattered about the residual plot. I mean, we just have zeros and ones, all the data lines up, depending on what the person is, if they're a member or not. So OLS is not a good idea for our study. We do have assumptions for the logistic regression, but they're so much better than an ordinary least squares regression. You just don't need as many, and it's very nice. Assumption 1 is that we need to have that dichotomous variable. So we score it 0 and 1. The outcome of interest is coded as 1. So for our study, our outcome of interest is being a member in the Tom Selleck fan club. So if you're not, you would have a code of 0. We want absence of outliers on the dependent variable. Basically, that means you should have all zeros and ones, right? You shouldn't have anything else on that. If you do, then you need to go back and fix up your data, find out what the true value would be. Absence of multicollinearity between the independent variables, and that is the same as in a regular regression. You don't want to be measuring the same thing with more than one variable. Independence of errors. That sounds really technical, but all that really means is that you don't have repeated measures in your study. So you didn't do a pre-test, post-test on the people. You didn't do a before intervention, after intervention kind of thing. It's not a longitudinal study. There are studies that do use a logistic regression framework in a longitudinal or repeated measures context, but we're not going to work on those today. We're just doing just a straight logistic regression. We need an adequate sample size. Some say 10 records per IV, others say 20. Others say 30. As with most things in statistics, it depends on who you ask, and it depends on your field of study. I say 20 is a good rule of thumb. Others might say something else. When in doubt, you can always run a power analysis. G-Power is a good software. It's free. You can download it off the internet. A lot of people will use that, especially dissertation. People will use, students, they'll use the G-Power. It's very useful. And it does have some options for powering the logistic regression and finding out what your sample size is. We've also done a webinar in the past on power analysis, and you can get that webinar and download it from our website. And I think it has a regular regression in it, not the logistic, but you'll get an idea of how to use G-Power, which is great. We don't use coefficients, as we use odds ratios in a logistic regression. So I said the OR is the abbreviation for an odds ratio. So I say that the odds ratio is the new B, right? We don't use them in the logistic to determine the direction and strength of relationship between the IVs and the DVs. We use odds ratios. And why is that? Well, it's because we don't have that linear incremental relationship between the independent variables and the dependent variable. Instead, we have probabilities. And probabilities are between 0 and 1, but probabilities aren't evenly spaced. If you think about it, the relative difference between a probability of 10% and 20% is 100%, right? You've doubled it. But when you get up on the higher numbers, between 80% and 90%, the difference is only 12.5% to go from 80 to 90. So it's not evenly spaced. Our outcome in logistic regression is dichotomous. The model measures the probability that y equals 1, your outcome of interest. So probabilities, they have to be between 0 and 1. Well, if you use a regular regression, oftentimes you will get values on your outcome or predicted values on your outcome that are above 1, or they might be below 0. I mean, they don't conform to what you could have for a predicted probability. And it's called non-conforming predicted probabilities, which means your outcome is greater than 1, and we don't want that. There are some, if you look through textbooks and such, there are a lot of formulas. There's a lot of reasoning of how to tear down that OLS regression and what steps are done to turn it into logistic. I'm not going to cover that today. I'm going to try to keep it simple. There's all kinds of information on the internet, and I'll give you some references at the end, and you can also look those up on, in your free time. And let's talk a little bit more about odds ratios for now. Odds. We should look at odds first and then the odds ratios. So odds are the probability of something happening divided by the probability of it not happening. Okay, it could be the other way around too. Okay, the probability of success, we're going to call that P. We're going to call Q the probability of failure. You also might see the Q written as 1 minus P. Again, since everything's between 0 and 1, if you have a value here for your P, then whatever's left over is going to be 1 minus that P, which will give you the Q. Okay. Then all you do is you divide them. Here's if you want the odds of success, it would be the probability of success divided by the probability of failure. If you wanted to find out the odds of failure, then you would have the probability of failure and divide it by your probability of success. So here's an example. The probability of me taking a walk tomorrow morning is 60%. I'll give it 60%, okay? It's January. I'm still a bit motivated, so I set it at that. So that would mean that the probability of me not taking a walk tomorrow is going to be 1 minus the 60%. So that would be 40%. So here's my odds of success, 1.5, and here's my odds of failure when I do the formulas, 0.67. Now we take those odds and we make a ratio. It's basically dividing one of the odds by the other odds. It's a ratio, fraction. So the odds of success we have here and the odds of failure here. So now we can compute this odds ratio either way, just like we could compute the probabilities and the odds either way. So the odds of success divided by the odds of failure is going to be this 1.5 divided by that 0.67, and we're going to get 2.23 for our value of the odds ratio. Okay. This means that I have over 2 times the odds of taking my walk tomorrow than not taking my walk. That's a good odds ratio for taking a walk, right? Because it's greater than 1. Now, if we did it the other way, if we're looking at the odds of failure divided by the odds of success, our odds ratio is going to be turned the other way around, and we're going to get a value of 0.45, which is less than 1. Now, this means that I have less than half the odds of not taking my walk tomorrow than taking my walk. Now, that's bad. That's a bad odds ratio for not walking tomorrow. It's less than 1, which means I'm about 55% likely to not take a walk. But that's good, right? I mean, I want to take a walk. So this can get so confusing. Like I put in my note here, they can be very confusing, especially when you're doing the odds of failure divided by the odds of success. It still kind of blows my mind a little bit. And so if it's any consolation, I still turn them around in my head, and sometimes I have to stop and really think about what do they mean. But today we're going to run our model, and I'll show you a little trick that might help you understand the odds ratio in the logistic regression context. So here's our question. What are the significant predictors of membership in a Tom Selleck fan club? The data we are using, I should let you know this, the data we are using is entirely contrived. I just made it up over the last couple of days. I did not perform an actual study. It's only for demonstration purposes. So it's just something I'm doing for fun. I just thought it might be a little more fun today. So I haven't gone into detail about the legits, and I told you that already. I haven't gone into the mathematical details, and you can Google that. I'm going to keep it fairly simple. So let's take a look at our variables. I have a data set, and it has 3,011 records in it. Each participant answered a few questions and also told us if they belong to the Tom Selleck fan club or not. So we coded our variables as follows. Here's our dependent variable, member of the Tom Selleck fan club. If they were, we coded them 1. If they were not, we coded them 0. Here's all our independent variables. We took their age, and I think it was somewhere between, I think it was 18 to 80 or something like that, but it's expressed in years. It's a continuous variable. Everything else, I think I made dichotomous. I didn't put an ordinal one in this time, but you can use continuous variables. You can use dichotomous variables. You can use dummy-coded, which is dichotomous. You can use ordinal, anything for a predictor. It's just a dependent variable that needs to be dichotomous. So I also have gender, and we coded, if they were a male, we coded them as 1, and if they were female, we coded them as 0. And you could code these whatever way you want, but you need to remember how you coded them, because when you do your interpretation, that's when it's going to matter. I said, well, Tom Selleck has a mustache, so maybe members of the fan club might have a mustache. So if they do have a mustache, they're coded as yes, and if not, they're coded as 0. Do they belong to the Johnny Depp fan club? So if they do, then they're coded 1 for yes, 0 for no. If they own a red car, not necessarily a Ferrari, but a car that's red, I coded it 1 as yes and 0 as no. Tom Selleck, I understand, has an avocado farm. So if they like avocados, I coded them as yes, 1. And if not, I coded them as 0. And of course, have you ever been to Hawaii? And I said, like, if you wanted to go on a trip, if you've lived there, if you've ever been there, coded 1 as yes, 0 no. Okay, so let's go ahead and run the model. I have the data set right here, Tom data. Here's Tom data. Here's the ages, here's gender, here's all the 0, 1s, right? And then, of course, age is continuous, just the age in years. Okay, let's go ahead and run this model. So let me get my notes here so I run it the same way as my notes. Okay, we're going to go up into the analyze, and we're going to go to regression, and we're going to go down to binary logistic. Okay, here's our dependent variable. I called it fan of Tom. And then I'm going to go ahead and put in all my independents, and I'm going to put them into the covariance box. So there's age and gender, and have a mustache, Johnny Depp fan, red car, likes avocados. Okay, right. We're going to choose enter. There's other options here, a lot like you would have in the ordinary least squares regression, but we're just going to enter them all at once If you have categorical variables, you will want to go here to categorical, and you will want to choose. I'll show you with this. However, I dichotomously coded them, so that's a way to get around this. But you could also go, if you say you did have ethnicity, maybe, and that's a nominal variable, so maybe you had 4 ethnicities. You could go in, you could take this, put it over there, and then down here you're going to choose indicator, and then you're going to choose, do you want the first value to be your indicator or the last value? Oh, this will be actually for your reference category. So you could code it accordingly. So maybe I would want the 0 to be the reference category, which is usually what I want, and that's why I do the dichotomous coding on these yes-no variables, is because I kind of want to force the model to do the 0 as the reference group, and then 1 will be the group we're looking at in reference to that reference group. And SPSS, left to its own devices, especially in these logistic regressions and multinomial regression models, it's arbitrary sometimes. I don't know why it does it, but sometimes it'll load up on one thing and not the other. So sometimes I just like to force it. But you can do this, and then you would just hit continue, and it would change it. But let's go back in and make it go away, because I'm not going to use that today. But I want you to know it's there. All right, so we did that. Let's see, what do we want to save? I don't think I really want to save anything here, but we'll go into the options. I want to get, let's see, what do I want here? I want to get classification plots. Gee, all these big words, huh? Here's another one. Hosmer and Lemma goodness of fit. We want that. I want to see if there's residuals, and I'm going to set them outside of 2 standard deviations. You could do 3. 2 is kind of nice, because you would expect quite a bit of your data to be inside 2. Anything above 3 is of course, your outlier. I want my confidence intervals. Let's see. I think I want an iteration history. And let's see. Case-wise listings, got that one. I think that's all I really need. And there's many other options. But like I said, we're keeping it simple. So I'm going to click Continue. And then I'm going to click OK. And it does its thing, and here it is. Okay, so here's our output. This case processing summary here tells you how many records were included in that analysis, how many were missing. So none were missing. It's a nice clean data set. Here's the way it coded it now. It's very, very important to look at this, because you want to make sure that if you coded your dependent variable as a 0, the internal value, which is what SPSS is using, is going to be 0. And if you have the 1, that the SPSS is also going to code it as 1. So you want to check this. Okay. Here's our iteration history. We're not going to worry about this too much today. Your -2 log likelihood is quite a bit like a deviance score. Normally we would use things like this. This is actually SPSS using it to try to fit the best model. Okay, and sometimes it'll run it over and over and over again until it sets on these odds ratio estimates or parameter estimates, until it's just such a little difference from one model run to the next, that it's going to set there and it's going to settle on them. So we only had 2 on this one, which is great. Here's our classification table. Actually, SPSS and a logistic regression, and most softwares, what they'll do first is they run 2 models. They run a null model, which means they didn't put any predictors in it. They just did constant, okay? And they just maybe classified everybody either as being a fan or not being a fan. Then there's a second model that is ran where it includes your predictors. And then what you're doing is you're taking that second model with all the predictors and you're comparing it to that baseline null, no predictor model to see if there's any kind of improvement in the percentage correct that we classified. Okay. This is your called your percentage accuracy and classification, this 50.8. So in this model, what SPSS quite often will predict in the null model everybody being not a fan. But this time, it predicted everybody being a fan. Right? So here's our predicted, here's our observed. So we're only in the null model looking at what the model, but that is predicting. It said, okay, I'm going to say everybody's a fan. Okay, so actually 50.8% were classified accurately as a fan. And I know when I set up the data, I kind of made them about half and half fans, half not. So that makes sense to me. And variables in the equation, we're not going to worry about that one too much today. Here's variables not in the equation, right? So this is the baseline model. So none of them are in there yet, okay? Now, here's block 1. Enter is the method that we use. So here's where we're adding them all, okay? Now when we entered them in, we had about 4 iterations before we settled on some parameter estimates. A lot of these with the log likelihoods and such you would use more or less if you're comparing different models. Say I made this main model and then I wanted to compare a model with one less predictor. Maybe I find a predictor that's not significant and I say, oh, would the model be better off without it? I can run it again and then I can do some computations on these -2 log likelihoods to see if there's a significant difference between models, to see if one's a better fit than the other. But again, we won't worry too much about it today. Your omnibus test of model coefficients is a test to look for your model fit, to make sure it fits well. We look at this. It's significant. If it's significant, that means that you have a good model fit. Okay. There's also this Hosmer and Lemishow test. If it's not significant, you have a good model fit. Okay, so here it's the sig is actually your p-value. So if you have a p-value above 0.05 on this test, your model's a good fit. So we're looking good on the model fit. Up here is a model summary. Okay, with the model summary, here's the one you would probably use to compare your 2 different models. This is -2 log likelihood. But you have these other ones here. How do I explain this? Whenever people regression, regular ordinary least squares regression was the first regression that most people used. And then they had an R-squared. And an R-squared is your indicator of model fit in an ordinary least squares regression. An R-squared, though, is derived from those errors, right? It's how much of that variance in your outcome is being contributed by all those predictors in the model. How much is that being accounted for? Well, we don't have linear here. We don't have variance here. We have predictive probabilities, right? So we don't really have an R-square. But there were some people, Cox and Snell and Nagelkerke and many others, said, well, maybe we can make something that's kind of like an R-square. It's a pseudo R-square. And so if you look at it, you can kind of read them the same. If I was looking at that and was using them, I would say, oh, wow, about 8%, according to this statistic, about 8% of the outcome is being predicted by the variables. And here, about 6%. And it's not very much. Certainly not 100%, and certainly not even close. However, most people do not like these pseudo R-squareds. I've had some reports where I put them in just to be conservative, just to report it, and had to take them out. There are people that cannot stand them. So you kind of use these with caution. They're pseudo. They're not actual R-squared. So I think that's the reason a lot of people don't care for them. They're just, like pretending to be an R-square. But some people like them. So you just kind of know your audience, I suppose, would be the thing to say on that. Okay, so let's go here. Here's our classification table with all the predictors, and here's where they were actually predicted, and here's where they were actually observed, and now they're all loading up nice and neat here on the classification. And I'm sorry about this little double click to activate. Someday I have to figure out how to get that to go away. But now we're at 59.6% accuracy, so almost 60%, and which is actually an improvement over what it was, which is baseline, which was about 51%. So we've gone up a bit. We've gone up about 8%, which is not bad. Okay, now here's the nice part here. All the variables that were included. Okay, now here's your B coefficients, and we're not really going to use those. And here's what we're going to use over here. This it's actually e to the b. If you take your calculator and you put hit that little e key and then raise it to the power of this, you will get this. And this exponential b is your odds ratio. Okay, so there they are. So what do we have that's significant here? We have age is significant, gender, and if you have a mustache, and if you're a Johnny Depp fan, Red car, doesn't matter. It's not significant. If you like avocados, it's not significant. But if you ever visited Hawaii, that's significant. Okay, so we have those. Here, I don't use this one too much, but what you would like is maybe to see your zeros down here more and your ones up here more. These are kind of in the middle. It's not going to make or break your analysis. It's just kind of a visual to let you know how things are predicting for you. And we also have it predicted at the 50-50 cutoff. So we had no outliers, so that's nice. Okay, well, let's go back into our PowerPoint. All right, so what are the significant predictors? So I already told you about the model coefficients and the exponential, raising them to e to the coefficient, right? So if you use your calculator, you can derive it, and here's the notation. So for gender, 0.652, if I take e and raise it to 0.652, I get 1.919. Boom, right there. So that's kind of nice to know. I thought that was the greatest thing when I found that out. Now, we have these odds ratios, and you're saying, okay, that's great. What do they mean, right? This I can kind of understand. For every unit increase in age, every year increase in age, I know my outcome would go up by 0.015, right, by a factor of 0.015. Not a lot, but it would go up some. Here I'm going, well, I have no idea. So remember when I said there's another way to interpret the odds ratios. We can do some computations and express them in percentages. If your odds ratio is less than 1, we're going to take the value of the odds ratio and we're going to subtract it from 1. And then we're going to take that result and we're going to multiply it by 100 to get a percentage. Okay, and this will tell you how much less likely you are, because it's saying less likely. So let's see here. The odds ratio for a person being a member in the Johnny Depp fan club was, where is it, 0.820, okay, which means they have about 0.82 times the odds of also being in the Tom Selleck fan club, and that means the odds decrease by a factor of 0.82. Wonderful. You write that in a report, and that makes all sense, but what does it really mean? And of course, this is all the variables being constant, right, just like in a regular regression, except in a regression, an ordinary least squares regression, when they're constant, they equal 0 for these b's. However, since it's a ratio, it's an odds ratio, it's one thing divided by another, you want it to be 1, not 0. So a constant would be an odds ratio of 1. So let's do the little computation. So if I take 1 and I subtract that odds ratio from it, and then I multiply it by 100, I get 18. And now we can interpret it as a person who belongs to the Johnny Depp fan club is 18% less likely to belong to the Tom Selleck fan club than someone who does not belong to the Johnny Depp fan club. Okay, so it makes a little more sense. It might still be kind of confusing at first, but I myself kind of have a better time wrapping my head around that and explaining that. If I say, oh, well, you know, if you belong to the Johnny Depp fan club, you're 18% likely to be in the Tom Selleck. You know, so that kind of makes more sense if you're speaking to somebody about it, or even thinking about it for yourself. Now, if your odds ratio is greater than 1, then we're going to take the amount of the odds ratio that's above the value of 1 and then multiply that by 100 and find out how much more likely in percentage. So let's see. Oh, I love this one. This one came out so nice. The odds ratio for a person having a mustache, 2.719. Okay, which means they have 2.72 times the odds of being in the Tom Selleck fan club than a person without a mustache, all other variables being constant. Okay, now the likelihood, I guess I don't know if I would call it a likelihood, but it's percentage. 2.719, and we're going to subtract 1 from it. Okay, then we're going to multiply it by 100, so we're going to get 171.9. Now we can interpret this as a person who has a mustache is about 172 times more likely to belong to the Tom Selleck fan club than a person without a mustache. And I said, wow. Yeah, so I thought that was pretty fun. Now there's more fun with classification tables. The one I showed you in the output, and I put a copy of it here, where in step 2, block 1, the classification table is all nice, set up really pretty. we can get a lot of statistics. We can get sensitivity. Sensitivity is the true positives, okay? And that means the people that are in the Tom Selleck fan club who were classified by the model, who were predicted to be in the fan club. So what we do is we just look at this number right here, okay? 63%. Not bad. True negatives is your specificity, and that means the people who are not in a Tom Selleck fan club were classified correctly in the models as not being members, and that's about 56.1%, and that's right here. Okay. Here's some more. Positive predicted value, and of the people predicted by it, of only the people that are predicted by our model to be members of the Tom Selleck fan club, the model correctly picked about 60% of them. So what we do is we take, okay, here's one where they were observed not to be a fan of Tom, but they were predicted to be a fan of Tom. Then we're going to divide it by these two added up together, which is the 1614 here. And of course, you always multiply it by 100 to get to percentage. So it's 57.79% of the people who were members were predicted by the model to be. And then you have your negative. Of the people predicted by the model to not be members in a Tom Selleck fan club, the model correctly picked 59% of them. And here we have our 831. They're not. And then they're divided by the total here. Right, 1397, yep. And so you have to look at it too again. And then multiply by 100, and there you have. Okay, and these are things that you can look up more. There's even more fun. So much you can do. But there are some computations that you can find out more measures of classification, except you have to do a little bit of changing on the table. Most tables will have it set up like this, where you have observed up here and predicted here. As you see, SPSS has predicted here and observed here, okay? And also they're backwards. Here's observed equals 1, observed equals 0, here it's 0, 1. So what we need to do is kind of change this table around to match this template. And so all I did was I just took the information. See, here we have, if we observed them as a 1 and the model predicted it as a 1, we have 965. So what I did is I just moved it, used this table here as a template, and here it is. I put it right there. So here's the same cell. It's just been moved around, okay? And the same thing here. So here they're not a fan of Tom, but they were predicted to be a fan of Tom. Okay, so here we go. They're observed. They're not, but they're predicted to be a fan. Here it is there. Okay, so you kind of do that and just fill in the blanks, move them around a little bit. If you do that, you can find all of these kinds of measures. Okay, and basically you just A, B, C, D. So you take whatever value here. It's like, let's see, what would be, let's look at the sensitivity again. So here's A. So we're going to have our 965. And then we're going to divide it by A plus C, which would be 965 plus 566. And you'll get the same answer we got from that classification table about 2 screens ago. So all of these things you can look at. And here's the odds ratio of the model right here. So you can figure that out also. And it'll match your SPSS output where you look at the actual model. You know, these are things that you could probably work on your own and play with a little bit and look up some things about all these different measures. But logistic regression is a lot of fun. I do like the odds ratios. They get they're a little getting used to, but I think they're a great model. Here's some references. We did cover just the basics, very basic. There's so many concepts and intricacies and different types and different ways of looking at things. So here's simple logistic regression. Here's a nice, these are nice plain English. I love them. The Biostat Handbook. And here's another one from the Biostat Handbook for multiple logistic regression, which is what we did today, more than one independent variable. Here's some more help explaining odds ratio from Karen Grace Martin at the Analysis Factor. Love her, great colleague. She's just an awesome person, brilliant. And her information is an easy read. She has great workshops. She has webinars. So you can check out her site. It's great. Sign up for some workshops. They're great too. And of course, you know I love UCLA and their IDRE. annotated output. Here you go for logistic regression, and you can look at the output that we generated today and read even more about it. All those tables I just skimmed over, you can go right back. And then, of course, if you're really interested and you're a big fan, you can look at this Facebook page. Tom Selleck's mustache actually has a Facebook page, which I just had to share with you. It's actually pretty fun. I think you'll get a kick out of it. Here's some events and offerings and such that we're having at Omega Statistics. You can read about this. We're going to send the PDFs, and we're going to send the data so you can play with this and generate all the things I did today and more if you wanted. We are going to have more webinars. I haven't thought about which ones yet because we are developing a new division, and I've been so busy with that. We have a lot of requests for APA editing. We have a lot of requests for data entry, transcription. Rather than keep that under our statistics division, I'm starting a new division called Clone, and I figured clones because we're cloning with data entry and transcription and such. I don't know how the APA editing fits in there, but I threw it in with it. We have the logo designed. We're working on the website, and I'm anticipating that to launch on March 1st. So, yeah, if you know people that need help with these services, we're the people to contact. So keep in touch. You'll get our monthly newsletters. You'll see you can go on our website, and we have a webinar link that you can look and see what's upcoming. And I probably the next week or so will put some webinars up for the next couple months. I might even go back and redo one that I've done before, some of the popular ones. But we'll announce them. So thank you for attending. And I think we do. We have about 10 minutes. Yay, we can ask some questions. So I'm going to unmute Brianna. And there you are. Are you there?
Hi, Elaine. Hi, everyone. Okay, so we did have a question. It was, which test would I use if I have a 3-category dependent variable?
It depends. If it's nominal, like just groups like red, yellow, green, or maybe ethnicity, something like that where it's nominal, then you would use that multinomial logistic regression that I briefly mentioned early on in the presentation. If it's ordinal, where it's like, say, maybe income levels. You have, level 1, level 2, level 3, like that, where it's going up incrementally, or maybe age groups or something like that, where it's ordinal, not necessarily nominal, but also structured, like an ordinal variable. Then there's actually something called ordinal regression. So it really depends. The problem with those is that they do require some more assumptions. So I don't want to go into it today, but sometimes you'll want to start with that multinomial regression. You go, oh, this will be great. You start checking your assumptions, you just can't do it. So you go, what you would do then is maybe aggregate into 2 groups and try to run your logistic instead.
Okay. All right, and then is it possible to just transform the dependent variable and use a regular linear regression?
That's a good question. Think about the dependent variable in a logistic regression. It's a 0 or a 1. Okay. A lot of the transformations that you use, you can't have a 0. Right? If you do a logarithmic transformation, you can't have a 0. You can't take a log of 0. Square root, can't take a square root of 0. Right? It just kind of falls apart. So really, if you do have a truly yes, no, either or kind of variable, you're better off using a logistic regression and deriving odds rather than trying to transform it, because then you'll have to do some things to your data just so you can save your zeros, like add 0.5 or something like that to the 0. You don't want to do that. You want it to either be a 1 or a 0. So that's my answer for that.
Okay, that makes sense. And then I have one more question. I ran a logistic regression and had a variable with a huge odds ratio and an even larger standard error. What does that?
Oh, okay. We didn't cover that today. Look up complete separation or quasi-complete separation. When you have complete separation, what that is saying is that your independent, all the value, like the values of your independent variable are all loading up on one of the categories on the dependent variable. Let's see, for instance, probably in our model, because I just kind of contrived the data. However, we did have that one variable, which was, do you have a mustache, right? that might cause a problem because, let me see if I can find it. Okay. We have gender and we have mustache. Well, mostly only men have mustaches, right? So you might have something there like a multicollinearity, which might be causing that inflation, okay? You also might have where maybe all the females are in the fan club. Of course, in this one, if you look at the odds ratio, since we coded the males as 1, actually men are about 91% more likely, or 92% more likely to be in the Tom Selleck fan club than women, because he's a man's man. You know, again, I just made up this model. However, it could be that let's say all the men were members of the club and all the women weren't. You're going to have what's called complete separation, okay, and that's going to inflate that. And to solve, to work with that, a lot of times the best thing to do is just take that variable out because it's just all loading up on one thing. It's not really predicting anything. It's almost like a constant. There's also something called quasi-complete separation, which means almost everybody loaded up on the 1 or loaded up on the 0, and there might be a couple stragglers, but it's quasi-complete. It's almost there. Like say maybe you know, say maybe they were almost all men and 2 women, you know, so something like that, and you'll still get that inflation. So anytime you get the huge, like I've had models where it's like in the millions on these, where your standard error will be really, really big and your odds ratio will be really, really big, go back and check your variables. Maybe run some cross tabulations, you know, and see if they're all loading up on one of those outcomes. Yeah.
Okay, that answers all of the questions that we received.
Oh, okay, good. All right, well, I guess that's all I have today. Let's see if there's anything else. Nope. So I want to thank everybody for coming. We had a pretty good turnout today, and I'll try my best to keep everybody posted on the goings-on here. And I hope you had fun. I hope you enjoyed it. I really enjoy doing this. Now it's almost I want to think about what kind of silly thing I can think of next time. I hope I helped you understand it more. That's the big thing. So and no more questions, then I guess we will just sign off, and I will get all of this out to you today or tomorrow so you can review it as much as you like. So thank you very much, Brianna.
Okay, thank you.
Okay, and thank you everybody for coming. Bye-bye.